Welcome to EDU World Space.
Let's prove part 1 of Theorem 8 in this section. And this says if the sum of an converges, then these two terms are equal. Here we're assuming, of course, c is just a constant, so a fixed real number. So to show these are equal, well, let's look at the left-hand side. So let's call un the nth partial sum of the left-hand side. So the left-hand side, we know that we can always rewrite the whole sum as a limit of partial sums. So, and usually you see it written in this form: the whole sum from 1 to infinity equals the limit of Sn. So here, in our case, we have Can. This is the entire sum going all the way up to infinity. Starting point might be 1, maybe not. But since it's not given, let's call it something. Let's call it 1. We can rewrite this as a limit of the partial sums here. Let's do actually, let me not call it S because we're using U. This is UK, the partial sums. So let's rewrite that partial sum. So here we can rewrite UK as CA1, CA2, all the way up to CAK, kth partial sum. This is just by definition of UK up here, partial sum. Then, since I'm just dealing with a finite sum, I can go ahead and factor out that c. And then I could also pull the c in front of the limit. This is just by one of your limit properties. So this is just using a limit theorem. When you first learned about limits. And then here, let's go to the next page. A1 all the way up to AK. However, this now is just Sn, where, so on the right hand side, we have this term here, and then we're calling Sn the sum of A1 as usual up to An. And then, therefore, we could go ahead and replace the limit of Sn with just the entire sum of An. And that's exactly what we wanted to prove. So this is our final answer, the whole argument.